Additive manufacturing production facilities have been proliferating all over the world, not just in the US, but really all over the world. And this leads us to the primary consideration of this presentation, which is, where is the most cost-effective location for AM production? So you may be thinking about setting up a production facility in-house. You may be thinking about setting up a service bureau, or you may be purchasing parts or sourcing parts from service bureaus. And it's very important to understand the answer to this question because it could give you a competitive edge. Depending on where you set up your production facility, you could get more cost-effective parts. Depending on where you purchase your parts, you could get more cost-effective parts. So a little bit about Senvol. My name is Annie Wang, and my partner is Zach Simkin, and we're the co-presidents of Senvol. Senvol provides analytics and consulting exclusively to the additive manufacturing industry. Our clients are threefold. One, Fortune 500 manufacturers, two, government agencies, and three, companies that are in the additive manufacturing ecosystem, such as machine manufacturers or material providers, and so on and so forth. And our core expertise is finding and bridging that middle gap between what is mechanically viable, i.e. what can additive manufacturing produce, with what is commercially feasible, i.e. profitable. So if you can find the intersection between what you can make and what you should make from an economic point of view, you can find business profit there. Finally, we're also very involved in the additive manufacturing community. We're proud members of America Makes. We're part of the ASTM F42 committee that sets standards on additive manufacturing. We speak at about a dozen conferences a year. We're also published, so for example, you can find us in the Wohlers Report. So going back to this world map, the question is, why would additive manufacturing costs even vary by location? Let's take two examples. You're in Dayton, Ohio, or you're in Beijing, China. Why would a part actually cost differently? And that's because the variables that go into those parts cost differently. The rent is different between Dayton, Ohio and Beijing, China. The material cost could be different. The labor cost could be different. And all of those variables affect the cost per part. So let's take a close look at some of the cost variables, starting with some of the non-additive manufacturing related cost variables. Things like rent, real estate, energy costs, labor costs, shipping costs. So shipping would refer to the cost of shipping that material from wherever you're buying it to your location. So for example, if you're purchasing your material from Europe and you have to ship it to the US, that's a certain cost. And of course, exchange rates. So if you are, say, located in the US and your supplier sells you in euros, you're subject to currency exchange fluctuations and risk between the euro and the dollar. There's also, of course, AM-related costs, and these are quite obvious. The cost of the machine itself, the cost of buying the raw materials, the ancillary equipments, so these would be things like sieving stations or the equipment that you need to maintain an inert atmosphere. Annual services, so these are costs that you would pay to your OEM for regular maintenance and warranties. Consumables, so for example, if you're running an SLS machine, you'll have things like filters and blades to worry about. And finally, post-processing. A lot of parts are post-processed. Examples of costs would be things like heat treatment, hipping, etc. So what we're presenting to you today is a case study that we did for the Government of Canada. And let me set up the case study for you. Imagine you have a production facility, and it has 10 machines, 10 identical machines. So we're looking at one type of AM machine being used throughout the facility, and that machine is running one particular AM material, and only one part is produced. So essentially, it's like a factory and it's just churning out these parts. The machine that we selected was the Renishaw AM250. The material that we selected was the Renishaw Tie 64, and the part that was produced was a part for aerospace. Unfortunately, I can't disclose anything specific about that part because it is proprietary to Renishaw, who was our partner in the case study. And finally, we selected 5 different locations around the world. There was Mississauga, Ontario in Canada, Dayton, Ohio in the US, Wharton, Lancashire in the UK, Tijuana, Mexico, and Beijing, China. And we selected these locations because they were locations where aerospace parts were being made. So let's take a deeper dive at the cost variables. Why is this important? It's because understanding how costs vary across the different locations leads you to understanding how much it would cost per part. So taking a look at energy costs, there's a huge variety of energy costs. The cost of energy in Canada is somewhere around 27 Canadian dollars per megawatt hours, whereas in Mexico it's almost 10 times that. There is actually a lot of detail behind this slide that I don't have time to go into, but I just kind of wanted to let you know that there is a lot of detail behind these numbers, but we'll be going over through the average costs. So this is the average energy cost. Looking at real estate costs, again, a very wide difference. Mississauga, Ontario being quite inexpensive at about 3.5 Canadian dollars per square foot per year, whereas Beijing, China is extremely expensive, partly because it's in an urban environment and China is going through a property boom right now. Looking at some labor costs, you can see that there's, again, a very wide difference in labor costs between the 5 different locations. The industrialized nations have much more expensive labor costs per hour, whereas Beijing and Mexico have much lower labor costs per hour. And of course, exchange rates. In this case, because we were using the Renishaw machine and the Renishaw material, all of that was coming directly from the UK, which means that regardless of where you set up that production facility, you would be subject to the exchange rate risk between your local currency and the pound. And finally, let's take a quick look at some of the AM-related cost variables. So just to set up this table for you, here we're going to look at some of the cost variables related to the AM machine. We'll be looking at some specific variables and then what units they're in, as well as some details, such as the minimum, the maximum, the mean, and the standard deviation. And we use that because we use a Monte Carlo simulation to run our cost models. So one example is machine life. Here we can see that a minimum machine life was 5 years, a maximum machine life is 15 years, with a mean of 10 years and a standard deviation of 2 years. And here's another example, which is a shipping cost from the UK to Mississauga in Canada. Unfortunately, I can't go through the specifics of a lot of the other variables, but we do take into account other shipping costs, the cost of the machine, the machine software, annual services, etc. Of course, we also looked at other costs that were other equipment costs, such as the cost of the chillers, the powder flask set, the sieving stations, as well as cost to calculate how much material were you using to manufacture the part. So that would involve things like part volume, part density, and of course the cost of the material itself. We also looked at the cost of the AM process, which includes energy. So these were costs mostly to do with time to preheat, time to build, time to cool down, time to clean your sieves, remove supports, etc. AM consumables, so a lot of these are things like the build plate, the wiper blades, the sieve mesh. And finally, we also took into account very detailed costs associated with post-processing. So these are mostly associated with the heat treatment and hipping, such as the furnace, the labor, energy, the argon gas, etc. So now I've gone through a summary of the cost variables. I'd like to ask Zach Simkin to come up, and he will be presenting the results to you.
All right, thank you, Annie. So as Annie went over, she talked about all the inputs, and all of these inputs experience variability and uncertainty. So for example, take labor rate. You could say labor rate is $40 an hour, but sometimes you might pay someone $37 an hour, sometimes it could be $42 an hour, and because there's variability with all of these inputs, the output, which is the total cost per part, exhibits variability, and the variability has different degrees of certainty. So all the inputs Annie went over were analyzed by the Senvol algorithm, and now I'm going to show you the output, which is the total cost per part. So we'll start by showing just Dayton, Ohio, and then from there I'll show you all 5 locations in one graph. So this is the results for the Dayton, Ohio, and you can see there's a range. So on the low end, the cost per part might be around $6,000, and on the high end it could be around $6,900. And for those of you that aren't familiar with the distribution, the areas that have a greater height means that those costs have a greater likelihood of occurring. So the highest likelihood is in this range around here, which is somewhere between $6,300 and $6,700, and the line in the middle is the mean. So the average cost per part in Dayton, Ohio, you can expect will be $6,450. So this is just for Dayton. And now I'm going to show you all 5 locations mapped together. So these are the results, and this is, let me walk you through this. So what you're looking at on the left here, the least expensive location was Tijuana, Mexico. So the average cost per part in Tijuana was a little over $5,700. Moving to the right, the next least expensive was Beijing, China, and that was around $5,900 average. And then the 3 industrialized nations all the way to the right are much more expensive. So that's the US, the UK, and Canada. And in this case, Canada was actually the most expensive production option at a little over $6,500 per part on average. And the really important takeaway from this slide, and it's very difficult to see, but the overlap in distribution from the Canada distribution and the Tijuana, Mexico distribution almost doesn't exist, which means that there is essentially a 0% chance that parts produced in Mississauga, Ontario, Canada, in this particular case, will be less expensive than the parts produced in Tijuana, Mexico. This is the same thing, but in a table, and what I want to focus on is really the differential. So we're looking at Mississauga, Ontario is $6,500 per part on average, compared to Tijuana at $5,700 per part on average, and Mississauga is over 14% more expensive. And when you talk about manufacturing, you often hear the term lean manufacturing. Well, a 14% cost differential in manufacturing is quite substantial. And what I want to talk about now in the coming slides is why. Why is Canada more expensive? What's really contributing to the fact that Canada, in this case, is more expensive than, say, Tijuana, Mexico? So on the y-axis here, you're looking at the total cost per part, and on the x-axis, you're looking at the 5 locations. And the different colors map to the contribution towards total cost of each of the individual cost variables. So an example, you look at this yellow or gold coloration here, that's the contribution of additive material cost towards the total cost per part. And you can see the material cost is by far the biggest contributor in all 5 locations towards total cost. However, Renishaw sells the material at exactly the same price globally, which means that although this is the greatest contributor, it actually doesn't contribute at all to the differential between the 5 locations. So the variables that contribute to the cost differential are the ones near the top. So it's your total real estate cost per part, that's the brown coloration, that varies by location. Next is the gray, that's the total post-processing cost per part. That's actually driven a lot by the labor costs of the post-processing. Next are your energy costs, that's this little sliver of maroon here. And lastly, perhaps most significantly, the total labor costs, the dark blue, that vary by location. And so this is a look at the same information but in a table, and what I really want to focus in on are 2 things. One, Canada actually has the lowest cost per part for energy and the lowest cost per part for real estate. So its energy cost per part are around $10, whereas Tijuana, Mexico is over 9 times that. Its total real estate cost per part in Canada is a little over $100, and Beijing, China is almost 4 times that. However, although Canada has the lowest energy and real estate costs per part, it has the highest labor costs per part. So its labor costs per part are over $640 contribution, whereas Beijing and Tijuana have much lower labor costs. And again, post-processing is the same story, and it's because of the labor associated with the post-processing. So the key takeaway at this point is that Canada's cost advantage on energy and real estate is outweighed by its disadvantage on labor. However, this is analyzing this specific case. So it's looking at the Renishaw AM250 with a specific material on a specific machine, making a specific type of part. What would happen if the entire additive process were to change? What if we had analyzed a different machine or a different process altogether? Might that change this equation on the top, and might that shift the tide in, say, Canada's favor? Accordingly, we looked at 2 what-if scenarios. So the first is, what if parts were produced using an additive process that consumes X times more total energy than the process we analyzed in the base case? So if the process had used 2 times more total energy, 3 times more total energy, might that shift the equation on the top and make the energy and real estate costs in Canada's favor outweigh the labor costs? Similarly, what if the second what if scenario is, what if the additive process would require X% fewer labor hours? So instead of the labor that was required, if it was 10% less labor, 20% less labor, might that shift this equation on the top in Canada's favor? So we'll start by looking at the first what-if scenario, which is the energy consumption. So on the y-axis, you're looking again at the total cost per part, and the x-axis is the energy multiplier. So this is saying if the energy in the whole process were 2 times greater, 3 times greater, 4 times greater, what would happen to the total cost per part in the 5 locations? And what I want to focus on is this. There's a crossover point at 8.1 times more total energy. So if the process we had analyzed used 8.1 times more total energy, Canada actually becomes the least expensive production option. So the tide has totally shifted if you're consuming more energy. And when you think about, are we trending in this direction? I would say possibly. So for instance, with laser machines, if you want higher power lasers or more lasers, that's going to consume more energy and shift you further right on this chart. This is looking at the same information, but in the bar graph. So this is at the 8.1 times more total energy, and this is the original analysis. So focus in on these maroon graphs here, the maroon little bars. That's the contribution of energy cost towards total cost. So this is the original, and that's at 8.1 times more total energy. So original, 8.1 times. And you see it's shifting a lot in the UK, Tijuana, and Beijing locations because their energy costs are higher. So let's reset, and now I'm going to take you to the second what-if scenario, which is what if fewer labor hours were required? So we're back to original energy consumption, original everything else, and we're only changing the labor. Again, y-axis is total cost per part, and the x-axis is the percent by which the labor required for the whole process had changed. So if you require 10% fewer labor hours, 20%, so on and so forth. And the crossover point here occurs at 90%. So if the process had required 90% total fewer labor hours, then again, Canada becomes the most cost-effective option. And when you think about, are we trending in this direction, I would say yes. Additive is becoming a more automated process. Post-processing is becoming more automated. Even things like sieving the material is becoming more automated. So I think we are trending in this direction. Again, a look at it in bar charts. So this was the original analysis. Focus in on the blue here. That's the contribution of labor costs. And with 90% fewer labor hours, you can see the labor costs become almost negligible. And at this stage, Canada and Dayton, Ohio are the most cost-effective options at around $5,500 per part. So I want to walk you through now just some summaries from this specific case study. And then on the next slide, I'll talk about some key takeaways overall, taking a step back from this specific case study. So the first is in the base scenario analyzed. That's, again, using the specific machine, specific material, so on and so forth. In this base scenario, parts cannot be cost-effectively produced in Mississauga, Ontario, Canada, compared to the Tijuana, Mexico, and Beijing, China locations. And this is because even though Canada has the lowest energy and real estate costs per part, that is outweighed by the fact that its labor costs are substantially higher than some of these other countries. But the story can change. So if the additive process were to require 8.1 times more total energy, then Canada becomes the most cost-effective option. And similarly, if the additive process were to require 90% fewer labor hours, then also Canada becomes the most cost-effective option. And taking a step back, just a couple key takeaways I want to leave you with is that these relative costs, all the inputs we analyzed, they change over time. So even the exchange rate has actually changed since we did this analysis and would actually shift things slightly in Canada's favor. So it's important to track all these variables and continue to redo this analysis, because you may do it today, but it could change in 3 months. The next is that in this case study, we only looked at the direct costs of production. But there in real life are many other cases, many other real costs you want to factor. This was a simplified case study, but there are other things manufacturers consider when you're choosing where to produce parts. And so other things you'll want to take into account are what's the stability of the energy grid in the location I might be considering producing parts? What's the availability of trained additive manufacturing machine operators? This can vary by location. The ability to protect IP also can vary by location. The availability of equipment required for post-processing can vary by location. And lastly, this is probably the most important, is that the location of your customer matters a lot. So we only looked at the cost of producing the part. We didn't look at the cost of getting that part to your customer. So we are not at all saying you cannot have reasonable and profitable service bureaus or production facilities in the US or Canada. In fact, if your customer is located in Dayton, Ohio, it probably makes a lot of sense to set up production in Dayton, Ohio, because you may save in production costs, $1,000 versus Tijuana, but if the shipping costs are over $1,000 just to get the part to your customer, that erodes all the savings. Also, you might have a lead time of 30 days, and so on and so forth. So we're not saying that production in the industrialized nations can't be cost effective, but when you factor in the location of your customers, again, that can shift the tide. And then lastly, what we presented today is a framework that you can use to compare costs among different locations. And you don't need to do this just to compare costs in different countries. You can even do the exact same structure to compare the different costs in different, let's say, different cities in the same country. And real quick, an aside, I just want to alert you guys to a resource that is on our website that is completely free to use. It's called the Senvol database. So it is a searchable database of all the industrial additive manufacturing machines and the industrial additive manufacturing materials that are on the market. You can search by over 30 fields, such as machine build size, material type, mechanical properties, such as tensile strength. So again, this is completely free to access. I encourage you to check it out. It's at senvol.com/database. And with that said, we thank you very much for your attention, and we will open it up to any questions.
Mm-hmm.